Explain how does the OH group attached to a carbon of benzene ring activated towards electrophilic substitution. So the first point you should notice, the groups which release the electrons in the benzene ring activate the benzene ring towards electrophilic substitution. And how does that happen? Why does that happen? See, electrophilic means electron loving. Electrophiles are the species which are electron deficient. So they love to go to those species which are electron rich. So if OH group can increase the electron density in benzene ring, we can say it has activated it towards electrophilic substitution. Does that happen? Well, it possibly might. Let's see how it might be happening. Let's take a benzene ring. Let me draw it more clearly like this. This is my good old benzene ring. Fine. And I have an innocent OH group attached to this benzene ring. You agree? Of course. Why not? And now, suddenly I find lone pair could be in conjugation with the ring. Oh my God, what do you mean? What I mean, my dears, is this. See, you could beautifully and nicely make these structures. You can say that the lone pair on oxygen atom has actually come down in the ring. And it is going all around. Actually, it is not going all around. It is going on ortho and para positions only. Fine. But it is going within the benzene ring. Of course it is. And as it moves within the benzene ring, I hope that you please note that the benzene ring has no option but to get more electron rich. Obviously, it is getting electron from OH. So lone pair from OH group gets donated to benzene ring, thereby making it more electron rich and thereby activating it towards electrophilic aromatic substitution. Let me add one more very subtle point to you. Let us try to write down the structures of two intermediates of electrophilic aromatic substitution. One intermediate when OH group is there and one intermediate when OH group is not there. That means, let's say we have benzene and let's say we have phenol. We have two different cases. And let us see, I'm just cleaning up some space for us to write. And let us see in which case we get more stable intermediate. I have benzene and I have an electrophile E+. I have phenol and I have an electrophile E+. In both the cases, see, electron cloud gets donated, right? What you get is the so-called rhenium ion or Wieland's intermediate. I get plus charge. This H is already there. H is everywhere. I'm just writing it separately so that it becomes obvious here. And if I have an OH group here, and I'm just as an example, I'm attaching this to the ortho position, the para position, like this. I get a rhenium ion. Now this plus charge can undergo delocalization here, etc., etc. And ultimately what I get is this. But do you notice that this carbon has incomplete octet? Yes. And watch the fun now. What? Just observe as delocalization happens. I can very well write down a contributing structures here. I can very well write down a contributing structure where no octet is incomplete, all the octets are fully satisfied. And octet rule is the major rule while dealing with second period elements. So I find that this is much more stable intermediate. Since intermediate is very stable, you find energy of activation comes down. And if energy of activation comes down, the rate of reaction as per chemical kinetics increases very easily and very rapidly. And that is the reason, my dears, that phenol is much more active towards electrophilic aromatic substitution as compared to simple benzene.